And okay, so we're recording now. All right, so this problem in question we're talking about right now is a limit involving sines. So the question looks something like this, and I'll modify the question a little bit so as not to give things away directly. But what's crucial here is that there's a sine on the top, and there's I'll call it maybe a 10 theta on the bottom, plus a tan theta as well. A 10 theta and a tan theta. Um, so the key here is to divide everything by sine. And the reason I am motivated to do that is because tangent is really just sine theta over cos theta. And we remember that the identity of theta over sine theta, the limit of this as theta goes to 0, do you know what this is? This is one of the key tricks in early calculus.
No, I didn't. I haven't learned that one.
That's perfectly okay. It's 1. And I'll give you a very, very brief intuitive explanation. But if sine theta looks kind of like this, right? It kind of looks like that. The idea is that if you zoom in a ton, like zoom in really, really, really far, let me draw it this way. So this is sine of x, this is sine of theta, and this is just theta, like y is equal to theta, right? But the idea is that if you zoom in really, really, really close, I can't zoom in any further because I'm limited by my screen, but they start to look like incredibly similar to each other near the origin. And as it turns out, the limit is actually quite exact. As theta approaches 0, the sine theta and theta themselves become almost exactly the same thing, arbitrarily close to each other, which is why the limit of theta over sine theta is just 1. So with that idea in mind, if we just divide top and bottom by sine theta, divide by sine theta, and we can do this because although it's approaching 0, it's not quite 0. So we're never quite dividing by 0, right? And as long as we're not dividing by 0, dividing top and bottom by the exact same thing is allowed because that's just the same thing as 1, right? Are you okay with that?
Yeah, when in the videos I watched, I got that you know how you did theta over sine theta equals 1?
Sure.
In the videos it said that sine theta over theta is 1. Is it like the same thing?
It is.
I don't know. That was what I was asking
It's a
because that's
perfectly
what
reasonable question, but let's just think about it, right? Excuse me. How do I put it? Yeah, it is, and this should be, I think, reasonably intuitive because it's just saying that what this really means is sort of saying that in the limit as theta goes to 0, sine theta and theta arbitrarily approach each other. They approach each other arbitrarily closely. So whichever one you divide by the other, it doesn't matter which one's on top or bottom, it's both 1. Is that okay?
Yeah.
Okay, great. We could prove that in more rigor, but this isn't a proof-based class, so I hope our intuitive explanation should be clear enough. But yeah, once you have that, well, okay, at this point, just take the limit as everything goes to 0. And do you think you can solve it from there?
Wait 1 sec. Let me catch up.
Sure. I mean, like, literally, I don't finish off everything. I just mean, like, do you feel like this is explained enough to where you can do the rest?
Yeah, 1 sec. Let me write it down so I could like understand because it's easier when I like have it down to like read it myself. So when you got 10 and times theta over sine theta, why wouldn't it be 10 theta over sine theta?
What's the difference between between the things you just
Oh
said?
yeah, sure. Actually, you're right.
Yeah. Are you
Yeah,
just
you're
saying like
right.
10 being on the inside of
No,
being in the
yeah, no, I
numerator?
realized.
Okay, sure. Yeah. No, I mean, at this point, we just talked about what this limit is, right? And the only other theta that appears here is in cosine theta. And that's a perfectly, as theta goes to 0, 1 over cosine theta is a perfectly nice number. So the rest of this you should just be able to crank out. Sound good?
Sorry, I'm just like pretty done.
Yeah, I'm gonna end the recording right there.